which is the threshold. I'm saying the threshold value, because for a particular diode this will be different, so I'm just taking it VF. And whenever I'm using a silicon diode, I will replace my VF with the 0.7 volt and whatever value is given in the numerical problem. And if I am using some other diode like germanium or gallium arsenide diode, then I will replace the value according to the threshold value related to those diodes. So I am just taking it as a VF value, and now I need to model this thing. So you can see here this model is little better model and ideal diode model, and in some literature you will find this is also called the constant voltage source model. Okay, constant voltage source model. So आप कंफ्यूज ना हो और फिर मेरे ऊपर आके एलिगेशन ना लगाएं कि ये सर ने क्या पढ़ा दिया, हमने तो कांस्टेंट वोल्टेज सोर्स मॉडल देखा था। तो ये एक ही नाम है, कांस्टेंट वोल्टेज सोर्स मॉडल। चलिए, now let us try to do the modeling. So in this modeling, all we need to represent this portion and this portion, and you can see here this is my diode now, and now I am using the second model, second approximation model, which is the constant ideal diode model plus voltage source model, or the constant voltage source model. So in this model, if I need to represent my diode VD and the current which is flowing inside the diode is ID, then I need to understand this thing, that the difference between this characteristics and the previous characteristics is just this constant value. If I add this constant value to this characteristics, then I can obtain the same characteristics. You need to understand mathematically. If this is some function, whatever is the function, let us suppose this is some function x, then all I need to add this value at this x-axis. So in this constant value, let us suppose the previous one was x, then the new one can be modeled, and the new one is the x dash. The new one can be modeled by x dash plus vf. Only we need to add this vf, because जहां पे भी इसकी वैल्यू x की जो भी वैल्यू रही होगी, बस वो vf टाइम्स बढ़ गई है। तो इसको मैथमेटिक्स को समझते हुए what can we do now? We can again this model this. So for this line, the diode is on. The diode is on, but the this line is vf ahead of the previous one. So in this modeling, I represent this voltage which I am using this voltage as this, like this voltage vf plus diode. Okay, so plus a ideal diode, because you can see this is the modeling for ideal diode. And if I keep the ideal diode modeling same, which we have learned in the previous topic, and I just add this value of voltage vf. If I add this vf, then I can definitely do the ideal diode modeling. So you need to understand this is the ideal diode modeling. Ideal diode plus constant voltage source modeling. Again, let me again explain you. Wait for a while. If you see this characteristics is VF ahead of the previous one. And mathematically, if my previous characteristics was X, let us suppose the function which I was representing is X, and now I have shifted my function to this VF value, then my new function is just X plus VF. So all I need to do model. So this. So how can I model? Now you need to understand step by step. How can I model this VF? This VF is certain voltage. We know that this VF is the quantity on the x-axis, which is a certain fixed voltage. So in order to model the VF, I need to use a battery, because this is the voltage here. So in order to model a voltage, so I need to use a voltage source. So I have used a voltage source, and the remaining part will be same. The remaining part will be same for the for the remaining part. The modeling is like just ideal diode model. Now you need to understand. So the in the ideal diode model plus constant voltage plus voltage source model, we represent the diode with a constant voltage source and ideal diode. And for the ideal diode, the modeling will be same. Now you can understand the ideal. If the I am representing this section, then diode is on. I can represent diode with a short circuit, because now you need to focus on, because we have compensated for this part. Now we need to focus on the ideal diode only. So if the ideal diode and if ideal diode is off, this is the on condition for the ideal diode plus voltage source model, and this is the off condition. Off condition when ID equal to 0, and here ID is greater than 0. You need to understand, and resistance is almost we have taken, because there is a straight line. There is a straight line. So R equal to 0, and here R equal to infinity. So this is how we can model in the ideal diode plus constant voltage source model. Wait for a minute. Okay, now we will come to the next model. So this is the model in which we replace the diode with a constant voltage source and ideal diode. And the modeling of ideal diode we have already learned in the previous topic of the ideal diode modeling. So this model is better. So now you can see this is little better. All we have left is the slope of the line which was like this. So we have the slope of the line. Definitely the line was non-linear. Definitely the line was non-linear, but we have approximated it as a linear. And in this modeling, we have not considered the slope. And now in the third kind of modeling, we will consider this slope also. Okay. And the third modeling is the best modeling, and it will be the best approximation of the diode. So now we will start the third model. The third model is ideal voltage source plus ideal diode model plus voltage source plus resistor model. So third model will be the resistor model. We will discuss the resistor model in a minute. For the third model, I need to redraw this line. Okay, for the third model, I will redraw this line. And the third model is the ideal diode model plus voltage source plus resistor. And this is the third one. Or in some textbooks, you will find this is also called the piecewise linear model. Piecewise linear. In this model, we also take the slope into the consideration. In this model, we also take the slope into the consideration, and model will be linear, because we approximate all those non-linearities. As I already told you, whenever we are modeling, that we are not taking all the attributes. And for the mathematical simplicity, we define the model, and we use mathematics in the model. So in order to modeling something, we need to consider the linear region, where the region is linear, so that with the help of mathematical equations, we can do the modeling. And it makes the life of electrical engineers easy, because otherwise doing the calculation with the diode equation, we will do the calculation, we will solve a numerical with the diode equation, and every time using the diode, non-linear equation would be very difficult. And whenever we are using the circuit, then definitely we will have to learn some numerical analysis, and we will have to use some tools like MATLAB, etc., or some software tools to find the circuit solutions again and again. So to make us simplify the circuits, we are doing this kind of modeling. So in this modeling, we represent this part as this. So here you can see this is again same, and here this is the on or conducting, and this part is off. And here we have considered the slope also. Now you need to understand if the slope. Now how can I model this slope? What is this slope here? What is this slope here? And if you need to understand, this slope is related to the inverse value of resistance. Here if you try to model this slope and use some mathematics here. So if I try to find this slope, then this is some change in current, and this is change in voltage. This is change in current, and this is change in voltage. So if this slope is, कोई पेन काम नहीं कर रहा. If I need to model this slope is delta I over delta V. This slope is delta I over delta V, and here you can see this delta I is larger as compared to delta V. Delta I is larger than here you can see with this slope, with this line, delta I is larger. So this slope is 1 by R, and R equal to delta V over delta I. So if I want to model this slope here, then I can model it with a very small value of resistance. You can see here this delta I here. This delta I is the change in current. You can see the change in current, and just by the basic coordinate geometry, you can understand this. That much basics of the mathematics is very necessary in order to understand the electronics. So you can understand it here. This delta I is the change in current, and this delta V is the change in voltage. And you can see this delta I is larger, far more larger than this delta V. And we know that this term is inverse of the resistance, as we have already modeled these things in the previous models. So now you need to understand this delta I over delta V is equal to 1 upon R, and this resistance is delta V over delta I, which is a very small value. So this slope can be modeled as a resistor of very small value. So I will use it as a RF. So now, if this model was X, again some basic raw mathematics. If this model, initial model, which was like this was X, and I have created a new like this. Now I need to take this part and this slope. I need to consider these two things which are extra now, this extra voltage and this slope, and which we have modeled as a resistance. So if I use a resistance and I use a voltage and the previous modeling, which is the ideal diode, then I can model this ideal diode model plus voltage source plus resistor model. So here we will conclude this thing. So this is how we can model. If this is my diode and I am using the third type of modeling, which is a piecewise linear model. Why we are calling this piecewise model? Because this is linear but piecewise linear. First piece is this OA, and the second piece is this OB. But I don't know why they are calling, because in the previous models were also these are also linear and piecewise. So but you will find this nomenclature in the books. So we do not have any problem with this as long as we understand what is the meaning of this model. Okay. So this is piecewise linear because this is piece OA is the linear, and plus minus, and this is VD, voltage across the diode, and this is the ID. And now we can model this in this kind of model by using a voltage source, constant voltage source VF, and a resistor, small value resistor RF, and the previous model of the ideal diode. So this is how we can model in the uh, third type of approximation, and this is the best approximation available for the diode. And if you want to write the on and off state for this model, then we will have to use this. This is the off state, and this is the on state. And one thing you need to understand, the value of this will be given. If it is silicon, then you will have to assume 0.7. If it is germanium, 0.2, 0.3. And if it is gallium arsenic, then the compound semiconductor, then it will be 1.2. And the value of this resistance is mostly neglected because this is very less. But if it is given, then you will have to use this value in the circuit, and you will replace our diode like this. We will replace our diode like this, and on the basis of the voltages, we will decide that this is conducting or not conducting. So we will use the ideal diode model. That's why you need to understand the ideal diode model, how we are modeling in the ideal diode model, how we are saying this is a on and off, and in the remaining two model uses this ideal diode model always, and some two again constants. In the second model, the constant is voltage source, and in the third model, the constant is voltage source plus resistor. Now, in order to make this thing more concrete and more clear, let us try to solve those numericals which we have solved for the ideal diode model with the help of remaining two models. Okay, those are very two basic numericals. So, with the help of ideal diode model, I will try to solve those numericals.